Лень.
Не, вот этот компьютер. Да.
Так, вы сейчас попробовали начать запись, я понимаю, да?
Да.
Угу. Ну как, записывает? О, Paul. Paul is coming. Hi, Paul.
Hi, Lonnie. How's it going?
Fine, fine. You didn't change much. No, I hope so.
Yeah, the COVID hasn't allowed us. We're all frozen. Yeah.
So, Paul, about your talk. Have you some prepared slides, and can you put it somewhere on the website for people may just scroll up and down if they want?
Oh, good idea. Yes. Yes. So I'll email them to you now. Yeah. Is that what you're suggesting?
Yeah.
Yep, that's it. So I'll send it.
Let me check.
Oh, no, I'm just sending it now. I just had to check that I was sending you the right file.
Google is great today to commemorate Memorial Day. Interesting.
Sorry, there's a holiday in America, you're saying?
Yeah. Oh, yes, I got it. Well, let me where can I actually put it? So let me just give me a couple of minutes to find out. Hi, Andrea. Oh yeah, people are coming.
Hey guys, good to see you.
Yeah. Let me just.
Hi,
Volodya, hi.
how are you? I spoke with Andrei. Unfortunately, it is impossible to change the time. Did you read my message?
To whom you are talking?
To you, like the organizers.
What time?
Anyway, if you didn't read my message, you don't know, because in Wednesday session is overlapped with Leonid Rybnikov very interesting talk in Skolkovo Vyshka conference seminar. So I just spoke with Andrei if it is possible to report the time of Rybnikov's conference. I mean, Rybnikov's seminar. But unfortunately, it is important because it is officially announced like a pre-defense.
Well, we cannot avoid all intersections. It's obvious.
Anyway, it's a pity that two interesting events are overlapped in the same time, in the same place, because both are in higher school of economy. That's the point. You are unable to avoid the overlaps with some other world seminars and conferences, but within the same university, it is.
Well, yeah, we cannot, will not change the schedule. That's, let's face it.
No, I see. I just try and didn't succeed. That's all.
Вова, Володь,
Yeah.
а ты принимаешь поздравления с окончанием трудовой деятельности?
Я еще не кончил трудовую деятельность. Я ее заканчиваю 31-го.
Okay, Paul. Important question. So Paul sent me slides of his talk. Where is the file? So where can I put it for people who are able to reach it during Paul's talk, scroll it up and down?
As usually you can put it in chat and everybody can be would be able.
Okay, so Paul, are you happy with that?
Yes, but if you put it in the chat now, you'll have to redo it in the chat, right?
No. I will do it after you start. No, not right now, of course.
Yeah, but yeah, it's a good idea.
Okay, so.
Paul, what time is it now in Melbourne? I don't hear you.
It's just about 10 p.m.
Yeah, and it's approaching 8 a.m. here.
Yeah, so I'm in a room actually next to 3 sleeping kids, but that's life.
You still have only 3. That's also was my question, actually, because you wrote that you have some small kids. I decided maybe some more.
I told you we're frozen at the moment. Things don't change.
Well, let me just go grab some coffee. I probably need it.
Володь, привет.
Всем привет.
May I contact you sometime
Of course.
soon? Well, when it's convenient for you.
Rather welcome.
I want to ask you about this Irina Bobrova.
Leonia asked me, okay.
Yeah, I know, yeah, but I want to ask mathematical things.
Okay.
Thanks. So when it's convenient for you? Like
after the last talk today, probably.
okay. So I will try to. So I may try to call you after last talk, right? Or
Just by Skype, you can.
or
call me.
Skype? Yeah, good. Thanks.
But we discussed slightly with Lenya mathematics options as well. So I think she's well suited, at least partly, to what you are going to discuss.
Yeah, Len told me. Yeah. Thanks.
Сереж,
Да.
ты бы меня тоже ко-хостом сделал.
Сейчас попробую. Это участники, да? А ты под псевдонимом Чехов?
Потому что я Леонид Чехов, да. Я не скрываюсь никогда. Честному человеку незачем скрывать, понимаешь. Ага, хорошо. То есть я то...
Добрый день, очень убедительно.
Добрый день.
Да. Леш, привет. Okay, so we have about 2 minutes to go. And Sergey, you will be recording, right? Or you're ready?
Recording is started already.
It start. It's automatically, and it's. I see it's go to the cloud, right?
Yeah.
Uh-huh. Okay, so hope it will work. $37. Well, I expected more people actually to come to this very nice Paul's talk, but hopefully they will. Oh, yes. 40. Olivia is here. Many people from all over the world. Sergey, don't you think it's time to start?
1 more minute.
Okay.
Just to be sure that
Yes, so here we have the beginning of Paul's slides. Okay, and now also important point, Sergey, is to make Paul a co-host. For Paul to be able to operate with his slides, right?
yeah, Paul is already. So you may start your opening speech.
It will not be long. Okay. So let's open the seventh conference, Combinatoric of modular spaces, cluster algebras, and topological recursion. It's in, as everyone knows, it's in a strange format this year, and we hope to be back to normal next year on the 8th conference of 2022, which will be actually a satellite conference to the International Congress of Mathematics. But it will be a year from now. And today, well, on the other hand, we can exploit possibilities of modern technology. And today we have three nice speakers: Paul Norbury from Melbourne. Okay. Andrea Brini from Sheffield, UK, and Lin-Huan Shane from Michigan State University. So we have three speakers from three continents. And so what we have. Yes, so that's technical stuff. That will ask Sergey Lando maybe at some point to switch off the sound of these people joining. We are happy people are joining us, but it must be better if they will join in silence. Okay, so let me continue just for one more minute. What else I want to say? I hope that many of you will enjoy the talks today and during this week, and we actually are looking forward to see all of you, or at least many of you, next year in person, because this conference also probably, as many people remember, have a another component besides scientific, but we'll try to make this scientific, at least this scientific component, to strive this year. And finally, just to say that it's organized by actually two newly organized structures. One is an international mathematical center at Steklov Mathematical Institute, and another it's International Cluster Algebra Laboratory at the Higher School of Economics.
Sorry,
So-
Leonard. Laboratory of Cluster Geometry. That's important.
Okay. That's your stuff, right? Okay. So it's my pleasure to present the first talk today, and actually it's not the first time the Paul Norbury is opening. Is the very first speaker of this conference. It was probably on the previous conference. Maybe it will become a tradition. We'll see. Okay, so Paul, now it's your turn.
Okay, thanks very much, Leonia, and thanks very much to the organizers for having this conference happen in this way. I'm looking forward to it, and thanks for the invitation to give a talk here. Today, I'd like to speak about the volume of the moduli space of super Riemann surfaces. The lecture is dedicated to Sergey Natanzon. I learned many of these ideas from his work. Okay, so I'll define the moduli space of super hyperbolic surfaces following in a character variety sense, following Stanford and Witten, but a character variety of a supergroup. And this character variety approach naturally gives rise to a measure which will enable one to define volume, and the volume will end up being finite. And the aim is to get a formula for the volume in terms of the cohomology on the moduli space of stable curves. So the moduli space of stable curves, these aren't super, these are just the usual curves. And there's two things going on here. It's not just the shift from the super to the stable, but it's also a shift from measure to something cohomological. So the volume of this super moduli space uses an Euler class of an associated bundle. So we'll see soon in the talk that the moduli space of spin curves is, or spin hyperbolic surfaces in this case, underlies the moduli space of super hyperbolic surfaces, and in fact lives inside the moduli space and has a normal bundle. So this will be the normal bundle of this moduli space that lives inside there. And this is all described via character variety. And this bundle here will be described via some, well, deformation theory, which is given by this first cohomology group. And on the algebraic geometry side, we'll deal with the moduli space as compactification of the moduli space of spin curves and a bundle that's produced via a different cohomology group. And the aim will be to, well, show that these, well, the restriction of EGN gives this new GN, and also to understand how a measure on the character variety side relates to, well, an Euler class obtained on the algebraic geometry side. And then consequences of such a relationship would be a relation with between intersection numbers and KdV. Okay, so the objects in this lecture, the moduli space of hyperbolic surfaces, which will be described via a character variety, and one can, on this character variety, via monodromy, deform the natural symplectic structure to get volumes depending on these lengths. L1 through Ln are positive real numbers. In terms of the geometry, we can think of these as lengths of geodesic boundary components of hyperbolic surfaces. And this volume and this moduli space of hyperbolic surfaces is related to the moduli space of stable Riemann surfaces. And the volumes can be given in terms of cohomology classes, specifically psi and kappa classes on the moduli space of stable curves, this compactification. And one can, well, Mesiconus used this viewpoint, this relationship between volumes given via a measure. When they were given via a measure, she managed to get a recursion between these volumes and volumes given via cohomology classes. And this gave relations between cohomology classes and enabled her to give a new proof of the Witten-Kontsevich theorem that relates intersection numbers on the moduli space with the KdV tau function. And in this lecture, I want to use the moduli space of super Riemann surfaces. So one can generalize objects from the usual moduli space to the super moduli space, but part of the idea too is to go backwards, use the super moduli space to understand features of the usual moduli space. In particular, use them to understand a different relationship of intersection numbers with KdV. Okay. So the definition of the moduli space of super hyperbolic surfaces. So these have been, this moduli space and the moduli space of super Riemann surfaces have been studied for over 30 years by people including Witten, Deligne, Frieden, Manin, Crane, Rabin, and more recently Penner and Zeitlin. And this description is due to Stanford and Witten describing it via this character variety. So we have the space of representations from the fundamental group of, this is a genus G topological surface with n punctures into this supergroup OSP12, which I've written below and I will say more about soon. And what I will say right now is that if you look at this inside the supergroup, it's looking like SL2R. So we'll see soon that there's a map from OSP12 to SL2R. And so the condition on these representations is this composition should be hyperbolic, and this up to conjugacy. Okay, so supermanifolds, on supermanifolds, we replace functions having values in the field, say R or C, with functions taking values in the Grassmann algebra. So let me just define these. So we take the exterior algebra of R to the N, and then a typical element is, well, if I choose a basis, it's given by these sums of wedge products. And this first element, known as the body of this element of the Grassmann algebra, is a real number. And when we take this limit, we break this into odd and even parts, and we could call them bosonic and fermionic. And so a first example of a supermanifold is Rmn, which simply consists of m tuples of even elements together with n tuples of odd elements. So we see in this OSP12 that these are A, B, C, well, all of these are even elements. Down here, this is an even element. The alpha and beta even elements, hence their product is an are odd elements, hence their product is an even element. And we see odd elements here. These are odd. These are odd because A is even, and even times beta being odd is still odd. And we can see that if we map this to A, B, C, D, but this body, so we're going to take for each of these even elements just the first real number, element of lambda 0, that this is an element of SL2R. So we have a map from OSP12 to SL2R. And now there's an action of OSP12 on the super upper half space, which is defined to be those elements in C11 such that the imaginary part of the body of Z is greater than 0. So C11 here, of course, we've replaced this field here, R by C, and we have CMN. And we have, if we quotient this upper half, super upper half space by gamma is the image of this representation into OSP12, this gives rise to a super Riemann surface. So a super Riemann surface is locally a supermanifold of type 1,1. It locally looks like C11, and it has more structure, which I'm not going to be describing today, but that more structure is a sub-bundle of the tangent bundle, a non-integrable sub-bundle. And this action here, this is the an action that generalizes the SL2R action, and it gives the OSP12 action on H hat. This preserves this sub-bundle, non-integrable sub-bundle, which I'm not talking about, but what it means is that this quotient here is a Riemann surface. So just to repeat, super Riemann surface. The super Riemann surface is locally C11 with further structure, and this action preserves that structure. So super hyperbolic surfaces are examples of super Riemann surfaces. Okay, so underlying these super hyperbolic surfaces spin hyperbolic surfaces. So SL2R double covers PSL2R. So this representation gives a hyperbolic structure. In fact, any representation to PSL2R lifts to a representation of SL2R. So it's common for us to, when we're considering representations into PSL2R, to consider those into SL2R. Anyway, but there's more information, and we'll see that it's a spin structure. So PSL2R is the orthogonal frame bundle of hyperbolic space. So that means, since this is a 2-to-1 cover, this is a spin structure.
Please yourself, those who join.
Yanya, I think you have the ability to mute him.
Yes. It just doesn't take 1 second, you know.
No, sure. No,
It's fine. It's fine now, Paul. Yes, it just continue.
Yep. Yes. So the spin structure, this SL2R, it's a double cover of the orthogonal frame bundle. So it gives a spin structure of H, and then this spin structure, well, this descends then under this representation to H on gamma. So a representation of the fundamental group into SL2R gives us a spin structure. Okay, it gives us more structure. SL2R, take the natural representation onto R2, and so this defines a bundle. This bundle lives over the quotient, sigma, and we give it the name T sigma to the half. So this is just a rank 2 bundle given by this SL2R action, and it's given the name T sigma to the half if we were to put a complex structure. It's not quite natural, the complex structure, but if we were to put a complex structure on this, then it tensor itself over C, and you would get the tangent bundle. Okay, and so what we've seen here is that this, from OSP12, this map to SL2R means that any representation into OSP12, any super hyperbolic surface, has an underlying spin hyperbolic surface. And more, we also have a section. So given a hyperbolic surface, I'm going to mute me for. Given a hyperbolic spin surface, notice that if we were to set these guys to be 0, so set these to be 0, 0, so all of this would be 0, and we set these to be in R, this gives examples of even elements, and so we get a map not only to SL2R, but we get a map from SL2R into OSP12. So representations into SL2R, which give us spin hyperbolic surfaces, give us very special super hyperbolic surfaces, a very special collection there. And so inside this, we have the normal bundle of MGN spin. And so we have this SL2R plus R2 maps to OSP12. And this now defines the normal bundle of, well, let me write it this way. So the normal bundle over strictly it's I of MG spin, but this is so the normal bundle, and this comes from this representation from R2. So it comes from, so what we do is we look at the deformation theory of this hyperbolic surface. This SL2R gives the usual deformation theory, and the R2 gives us the deformation theory in the odd directions. And so what we find here is that the dimension of MG n, which is given by the dimension of the first cohomology of the tangent space, which is, this is say H1 of the tangent space of the hyperbolic surface plus H1 of this associated rank 2 bundle, and this is equal to 6g minus 6 plus 2n, 4g minus 4 plus 2n.
Sorry, Paul, is it a real dimension?
Yes. Okay, so our holomorphic description of spin structures, we take a square root of the canonical bundle, and this canonical bundle, so this is actually true for sigma compact. We're going to be interested more generally in sigma punctured, but for the moment when sigma is compact, we take square roots of the canonical bundle, and then we have the dual of L is isomorphic to this bundle. It's just given this name, the tangent bundle to the half, but it's really coming from the real definition is it's come from this representation, this SL2 representation. And so these two facts use the compactness, and what we when sigma is non-compact, we need to take, well, I'm thinking of sigma is equal to a closed topological surface minus a collection of points. And so we take the compactification, and we need to take the log canonical bundle. And then we don't have such a nice isomorphism. There is something I could write down, but it gets twisted by this divisor. But the reason I don't want to write it down is there's more structure here that I won't be saying too much about, and that is this curve will have some orbifold structure. And so we'd need to be relating a push forward of this line bundle with T sigma, but we can consider the compact part. And so that what we've got out of this is that the conclusion is that H1 of T sigma to the half defines this normal bundle, which lives over mgn spin, and we have this holomorphic viewpoint where we would like to put inside here H1 of this L dual, and that's what I'll discuss next. Okay, so, and maybe I should say why. So later, just down here, we're going to be defining volume via a measure using the character variety. So on this side here, we have a volume used by Stanford and Witten. So that's this side here. This is the Stanford-Witten volume. And we're going to, where the aim is to get a cohomological description of this. And this is what we're aiming for. We're aiming to get this type of isomorphism. So I need to describe these different cohomologies. So first of all, even in the compact case, when these two bundles are isomorphic, these are very different sheaves. So this left-hand side here is the sheaf of locally constant sections, and this right-hand side is the sheaf of locally holomorphic sections. So just to demonstrate how different they are, for example, if sigma is non-compact, the sheaf of locally holomorphic sections is trivial, whereas it's non-trivial in this left-hand case. So there's a few issues to describing this isomorphism. One is that they're different sheaves, and two, actually this right-hand side here is living over the compactification. But this is the type of isomorphism that has existed in other situations. For example, the usual moduli space of curves we would be looking at on this left-hand side to replace this T sigma to the half, we would be looking at the flat bundle associated to the Lie algebra SL2R, and on the right-hand side, we'd be looking at the tangent bundle of this sigma, again, twisted. Okay, so let me tell you about the cohomology. So we take the sheaf of locally constant sections on a bundle E. So I'm thinking of E as being this T sigma to the half, but I'm also thinking of E being the coming from, how do I write this? So this comes from the representation of SL2R on R2, but I'm also thinking of the representations of SL2R on its Lie algebra and also on OSP, the Lie superalgebra. So let me just say OSP 1, 2. So this E is any flat bundle, and I'm thinking of these 3 examples, but mostly this example here. But given any flat bundle, this F is this sheaf that takes an open set and gives you the locally constant sections, or the flat sections, if you wish. And so we take the boundary value of these flat sections on some simplex and just restrict it to the boundary of this simplex, and we get now flat sections on the boundary. So this forms a complex. And in the case when E is equal to this rank 2 bundle, if the representation is hyperbolic, one can prove that the second homology and the 0th homology vanish, and the first homology is given by this. So this first homology one can use, for example, dimers to do this. So one can triangulate the surface so that the one cells have what's the graph what's known as a dimer, and you can use this dimer to get a trivialization of this. Okay, so look, I'm calculating homology, but this is dual to the de Rham cohomology. So this is a calculation and explanation of what this dr or de Rham cohomology is. And now on such a complex of associated to this sheaf of locally constant sections, there's one can take torsion. So torsion is it's a measure. It's just a top form on the vector space, and one can use this to get a measure on the moduli space, or really on the tangent space. So we get a measure on H1. So a measure on, really it's the, well, it's a measure on this moduli space, but it's a top form on the tangent space. And so this produces a definition of a volume of the supermoduli space, integrating this measure. And this uses the, well, at the moment, this measure here is using this representation, but this representation splits on this normal bundle to SL2R plus R2. And what this leads to is it's also given by this expression here. One can calculate it via an integral over the moduli space of smooth spin hyperbolic surfaces and take the Euler class of this normal bundle times the measure coming from the Weil-Petersen symplectic form.
Paul, is it true that M hat is still non-compact?
It's non-compact. As for it being Kähler, so I guess I don't understand what a Kähler super object is. So, but it's non-compact for 2 reasons. If I was to compactify the base, it's still going to be non-compact in these odd directions. But this is non-compact in the odd directions and also in the base. But I'm sorry, I'm not addressing the Kähler part of that.
Thanks. Yeah.
Okay, so this is the definition of volume using a measure, and we're interested in a definition via cohomology. So you know, idea would be simply that one takes the Euler class of a bundle and takes an Euler class and uses the cohomology. But one thing that's probably worth pointing out immediately here is that, of course, this Euler class lives in H to the, 2 to the 2g minus 2 plus n of mgn spin, but this is equal to 0. So this Euler class is a measure. This is also true for the moduli space, the usual moduli space of hyperbolic surfaces. When we look at the top volume, it's the cohomology class. There's no cohomology up there, so we instead use a measure. So what one could do is one could take a relative Euler class, or one could extend this bundle nu gn to a compactification and take an Euler class. And that's what we'll do, but then one needs to know it's the right extension. Okay, and so look, this is just a brief description of how we relate this bundle here. This bundle EGN is defined over the compactified moduli space with fibers this cohomology. And I've said this cohomology is rather different. It's this sheaf, sorry, the sheaf is rather different. It's the sheaf of local holomorphic sections. So the way this is proven is, in fact, to follow Hitchens' proof of uniformization using gauge theory. So take the bundle of spinors. The bundle of spinors has this description here. It's exactly this rank 2 bundle tensor C2, which means it's just this flat bundle where SL2R is acting on C2 in the natural representation. Or it's given by the sum of these two holomorphic bundles. And in fact, Hitchens starts with this holomorphic side, some of these holomorphic bundles, and shows that this is stable. I'm hiding a Higgs field. It's actually a Higgs pair, and it's stable as a Higgs, as a pair of the bundle and a Higgs field. But it's stable, and so on this, one can prove, or Hitchens can prove, that there exists a flat connection. So this flat connection exactly is giving us this. So let me see. Hitchens starts here and uses this theorem to prove that this is flat, and this is flat is giving us, and it's an SL2C flat structure, or SL2C flat connection, and then there's a real structure on this bundle which gives us an SL2R. So this gives a proof of uniformization, saying giving a conformal structure on a curve, one can find a hyperbolic structure. That flat connection is exactly the representation into PSL2R that's required, but Hitchens actually gets a representation into SL2R, and so gets extra structure, this spin structure, and it's precisely what we need. So there's a theorem of Simpson that relates these two types of cohomology, the Durand cohomology and the Dolbeault cohomology, or what he calls the holomorphic Dolbeault complex, and the cohomology of this. Again, not defining this. This is using the Higgs field, which I'm not describing here, but this is some cohomology of this rank 2 bundle. So in this case, these guys essentially equal these guys here. This S sigma is just the is T sigma to the half. S sigma comes with the real structure. So even though it's a rank 2 complex bundle with this real structure, it's indeed this rank 2 real bundle. And now these two here aren't simply going to be the same. This S sigma is now a rank 2 holomorphic bundle, and one needs to calculate this cohomology that involves the Higgs field. And what it turns out to give is the yeah, I think I see a mistake just here. What it turns out to give is this cohomology giving this isomorphism, this cohomology of this holomorphic bundle. But I think I would like to say that we're working over this compactification. So, well, actually, sorry, this is for, now I see why that was correct. If this is non-compact, so that's in the compact situation, that's what Hitchens dealt with, but Biswas and collaborators instead for, so this is for sigma compact. When sigma is non-compact, look, this is just a detail, but maybe it won't take long just to mention it. One, instead of taking this S sigma, we need to, that is this guy here. We need something else. And so we take this T sigma to the half twisted by this divisor, which is the difference between, so if I take sigma bar minus D is equal to sigma. So this is just a collection of points P1 through Pn. And I guess I'm mentioning this non-compact case because this isomorphism is between these cohomologies is interesting. Even when sigma is compact, this is non-trivial again because they're entirely different sheaves. But when sigma is compact, it's non-trivial. But when sigma is non-compact, it needs to deal with these different sheaves and it needs to compactify. And so this now uses parabolic stable pairs. No, it's not stable pairs. Parabolic bundles with Higgs fields. Okay, so to summarize what's happened there is what we have is we have a definition of a volume that uses the character variety, and that uses a measure. And we now have, well, I should give the punchline, I guess. There's no, so the punchline here is due to this isomorphism is that here, therefore, if I restrict this to MGN spin, to the smooth guys, then this is isomorphic to this bundle. So we have this bundle which extends nu GN to the compactification. So we would like to take an Euler class of this bundle and say that this gives the volume because the Euler class of nu GN gives that. But again, we really need to show that the measures obtained are the same. So if we just take an Euler class, there are many extensions of this bundle, so that's not good enough, but that's what I'm going to do for the moment. So just take this Euler class here. So I'm going to define now this volume given by, well, let me, this at the top, we'll describe it instead down here first and then come back to that. So we take this compactification of the moduli space of spin curves. These curves here have some orbifold structure, and they're given this a square root of the canonical bundle with this isomorphism. And there's a bundle over this compactification given by, well, defined to have fiber, the first cohomology of the dual of this square root of the canonical. And this bundle gives a nice extension by this previous result. This gives a nice extension of the nu GN, but not the only extension. And then we push forward this, the top Chern class of this bundle, this would be the Euler class, to the moduli space of curves and normalize this. So this is just some normalization. And this now gives us a class in MGN bar. And when we integrate over MGN bar spin, it's the same as integrating the push forward. So this is what we're working with. We're working with these classes theta GN, and we'd like to define this volume by integrating this theta GN next to the exponential of the 2 pi squared of kappa 1. So this is analogous to the, well, let me write that this here is, gives the cohomology class of the extension of the Weil-Petersen symplectic form to the moduli space of stable curves, to the compactification. And then when we add these terms here, this gives us this symplectic deformation. And so this is simply a definition. And Stanford-Whitten wrote that these are equal, but this is, there's some still, well, this is exactly what this lecture is about. There is still some foundational aspects to get right there. So, but this is the issue. We've defined this and we'd like to know that it's the same as this. Okay, these classes, theta GN, they can be characterized just down in the moduli space, stable curves itself. So without a memory of its spin origins. And so here we have this map. Rho is given by this map here, the map phi, so given by this codimension 1 stratum sitting inside MGM bar, and the maps phi given by where this I is telling us how these N1 points interact with the N points. And then we have this forgetful map pi. So what we have is that these classes, theta gn, are natural. They restrict naturally to these codimension 1 stratum and pull back naturally using the forgetful map. And then there's this, well, initial condition, we could say, or just a calculation. In the 1-1 case, this is 3 times psi1. And so by a result of Faber and Pandarapande, which strengthens a result of Louis Henga, we can calculate all of these intersection numbers of theta gn with any polynomials in the kappa or psi classes. These are uniquely determined by these 3 properties. So it's an inductive argument, and this 3 is the initial condition. And from this, we can, via the result of Faber and Pandarapande, what it does is it expresses any polynomial of degree g-1 in the kappa classes in mg bar 0. Well, it doesn't express it. It gives the existence of it's a boundary class. And so what this does is it inductively reduces these intersection numbers to simple intersection numbers all the way down to the genus 1. I guess I haven't said, but maybe I should write this, that in genus 0, they vanish. So theta 0 n is equal to 0 for all n, and that's simply because 2g minus 2 plus n is greater than 3g minus 3 plus n when g is equal to 0. So this class just lives outside homological range. Okay, so what this means is that this volume here is calculable. So this is calculable. We would like it to be the Stanford-Witten volume. So this volume here consists of, well, I've said this one at the top, but I'm thinking more generally of this one here. This one here gives these theta g n's against polynomials in kappa and psi classes, and that's exactly what we can calculate. Okay, so I'd like to just summarize. There's a little bit new here regarding the Hermitian metric, but I'd just like to summarize. So what we have is we have this moduli space of super hyperbolic surfaces. We can deform this, the measure on this given these n lengths. So what we have is we have these spin hyperbolic surfaces with n boundary components, and the lengths of these are fixed to be Li, and these live below these super hyperbolic surfaces. And the volume of these is defined via, by Stanford and Witten via this measure, and it's given by this expression. And I've pointed out that we can't think of this as cohomological because this cohomology class would vanish. It's just in the wrong degree. This is a measure, and indeed this is precisely the way this is set up using this character variety. The measure is the natural object. And I've defined these volumes here, and these volumes using this algebraic geometry and this compactification. And we also have this fact that this is equal to EGN restricted to the smooth part. So EGN is an extension. Of nu GN. Okay, so how could we show that the Euler class of EGN is the that's a cohomology class, gives the correct Euler class, this measure on UGN. And so what we would need to do is we need to express the Euler class of EGN as a measure and compare these. So there exists a natural Hermitian metric and connection on EGN. So EGN is entirely analogous to the bundle that gives us the moduli space, the usual moduli space of hyperbolic surfaces. So one uses the hyperbolic metric to, basically I'm giving the definition of the Weil-Petersson form. The Weil-Petersson form on the moduli space uses a natural metric on this deformation space. So this is a deformation space in the vertical, in the odd directions. That's saying it in super language, but it's also a well-defined bundle, whether or not we acknowledge the super odd directions. But this is analogous to the bundle which has fibers H1 of T sigma used in the construction of the Weil-Petersson metric. So just as this has a natural metric, this EGN has actually essentially the same natural metric. They're different bundles, but they're getting it from the same place, from the hyperbolic metric. And so this means that once we have a Hermitian metric and a connection, so the Hermitian metric actually gives rise to the connection. A Hermitian metric and a connection on a holomorphic bundle are equivalent. Given a Hermitian metric and a holomorphic structure, we get a connection. So really what I just discussed before was the existence of a Hermitian metric that gives us this connection. And now given this connection, we naturally get a differential form, which is a measure representing this Euler class of EGN, this top Chern class. And so still open problem, when I say still, because I've been working on this for a while, I'd love it if others could solve this, that under this isomorphism, VGN is isomorphic to EGN on the smooth part, this measure coincides with the Stanford-Whitten measure. So there's lots to work on here. I mean, there's lots of places to go with this because the Stanford-Whitten measure, this torsion is very calculable. And this is this natural differential form and measure is also, well, I don't know that I'd say calculable, but let me say it this way. The fact that Wolpert, what Wolpert did on the usual hyperbolic space, showing that the Weil-Petersson form is related to the kappa class, these types of techniques can make this Hermitian metric here is rather, I guess, friendly. So anyway, I feel that this open problem, the answer is that they are isomorphic and it's provable, but I can't do it yet. So I just want to spend just the last bit, the lecture, with consequences if this could be proven, because it's rather pretty. It involves Mesiconus' work. So Mesiconus proved this volume recursion for the usual Weil-Petersson volume. So here's the usual Weil-Petersson volume. So we take the exponential of the Weil-Petersson form and integrate it either over the moduli space of hyperbolic surfaces or over the this moduli space of hyperbolic surfaces with boundary, geodesic boundary components of fixed length. So this gives a deformation of this. And this now uses Wolpert's result. Wolpert, again, I've said that, I'll write it here again, but this is the given, I'm writing this, but really I mean the extension of this symplectic form to the compactification and its cohomology class. That's equal to this. And so these two expressions for the volume and this recursion that I'm about to describe of Mesiconus gives now a recursion between these intersection numbers, these kappas and psi's. So here's Mesiconus recursion. So what's important to look at is that there's some simplification going on. Here's the volumes for Gn, and they're given in terms of simpler volumes. So this is Vgn minus 1, and the Pgn has also simpler volumes. And this is, one obtains this VGN via integrating these against kernels, and I'll discuss the kernels in a moment. What I want to do is describe the Stanford-Whitten. So Stanford-Whitten proved, again, there's some features to be filled in what they have to say, but basically this is, so it's just some foundational aspects to the proof that need to be, but this is, I guess there's still some more hats to be put in. So it's exactly the same recursion. Well, it's the same simplification here, and except that these kernels are different. So this is the Mesiconus, the Weil-Petersson volume. So given this recursion and these two initial conditions, so these two are initial conditions, then one can now just calculate using this, all of these. And then for the Stanford and Witten, one can calculate, I have them written on the side here, one can calculate that, or V03 hat, this is 0V11 hat is 1/8, which is equal to V12 hat. One can calculate all of these. I'm just giving you the smallest ones, 9 on 256, 4 pi squared plus 1/3 L squared. So this is the degree of this is 6g minus 6 plus 2n, and the degree of this is 2g minus 2. In particular, you can see genus 0. They don't, they vanish. Okay, and so now just to point out these kernels. So this is the kernels by Mesiconus. So this is the D and the R without the hat. So D is given by, there's this kernel H and DDX. So the partial derivative of D is given by this H, and together there's an initial condition. There's the vanishing of D at when X is 0. And similarly here, this uniquely determines R, there is along with an initial condition. And the kernels used by Stanford and Witten look very much the same. So again, that's the only difference between these recursions. Mesiconus and Stanford and Witten have exactly the same recursions, except for the difference in these D hats. And of course, I guess the initial conditions, the initial condition V1 hat. And so here we see that the H's are rather similar. The D and the R looks like it's defined in the same way, except it's missing partial derivative. And so in particular, we don't need some initial condition here. But these are essentially the same. And both of them come from understanding a pair of pants. So Stanford and Witten understand a super pair of pants, and Mesiconus has an understanding of a super hyperbolic pair of pants, and Mesiconus has an understanding of a hyperbolic pair of pants. Okay, so Mesiconus, with this recursion, reproves this Kontsevich-Witten theorem, and that is that this generating function for the intersection numbers of the psi classes is a tau function of KdV. So her proof, again, what it does is it takes the volumes, defines them via measures, and with these measures she can get these recursions, and then relates that to the algebraic geometry, which will give recursions for, well, she'll get recursions for combinations of kappa classes and psi classes, but she can from that extract these relations between just intersection numbers with psi classes. And similarly, this recursion of Stanford and Witten, if I instead replace this with these theta, VGN theta volumes, if you recall, they should be equal to the Stanford-Witten volumes. Maybe I shouldn't scroll too much. They should be equal to the Stanford-Witten volumes, but they're just defined using the algebraic geometry. And so this is exactly the Stanford-Witten recursion, where we're using the D hats and R hats of Stanford-Witten. And the statement is that these following two statements are equivalent. That if these super volumes, say, using this theta class, satisfy this recursion, then this generating function for these intersection numbers is a tau function of the KDV hierarchy. In fact, a known tau function. Oh, sorry, I was going to scroll for I've reminded us what these volumes are here. And conversely, if these satisfy this, if this is this tau function of the KDV hierarchy, this is the Bresson-Gross-Witten tau function, then this recursion holds. And so then the idea would be if we could show, and many of the steps are in place, that these volumes are the same, is the same as the Stanford-Witten volumes defined via measure, and the recursion of Stanford-Witten is rigorous. Again, there's just some foundational aspects of that. Then that would give proof of this second statement here. Okay, I'll finish that.
Okay, so thank you, Paul, for a very illuminating talk. So let's thanks Paul first time. And questions, of course. So please feel free to unmute yourself and ask questions.
Paul, have you checked that the second assertion in the theorem is indeed true for some small numbers or small values of G and N?
Yes, so this second assertion, I used to have a proof of it, in fact, until Vincent Bouchard found a gap in the proof. And so it has been checked for all N for genus up to 5 or 6. And there's actually, this is one proof of, one potential proof of this fact. There's a number of potential proofs of this second fact here. So I'm confident that this second fact is true.
Thanks, yeah.
Okay, of course. More questions first.
I have a small question. So in Mirzakhani's proof of her recursion, these kernels D and R, they have a specific geometric meaning. They are like the portion of the first boundary from which you can shoot an orthogeodesics, and that is defining a certain pair of tens. Is it the same in for this D hat and R hat? So can you talk about like ortho super geodesics or these kind of things?
So yes, it's the same, although Stanford and Witten had to deal with exactly your question. Can you talk about orthogonal geodesics? You can't talk about orthogonal geodesics. And so they have to replace what, so exactly that's what they want to do. They want to start at a, so just for others, your question has been, if I say start at this boundary and I shoot out geodesics and I want to know, for example, when do I finish at this boundary? And this is going to give me an interval on this of all those geodesics that would meet that boundary, for example. So this notion that you'd start there and take these orthogonal geodesics is, they need to understand what that would mean in this case. So they need to take, along with the geodesic, there comes a second, like a plane that comes along with it, and they need an intersection of some such things. So, but in fact, they're doing, their analysis of the pair of pants is the same as Mesiconus' analysis, except this notion of, well, in fact, intersecting geodesics. So maybe I'll just say one thing that should make sense. This is coming exactly from Stanford Witten, that geodesics shouldn't intersect in this dimension. It's a 2-2, real 2-2 supermanifold, and geodesics should just miss. And so the notion of even intersecting geodesics, which needs to occur in this Mesiconus analysis, one needs to have a different understanding of that.
Okay.
Could I ask another question?
More questions?
Can I ask a question?
Yes, Ken.
Okay, so is there any way to insert fermionic punctures or marked points in this formalism?
Insert fermionic functions at marked points.
Yeah, or like maybe you have, so N basically refers to bosonic marked points. And is there any way to insert fermionic marked
Sorry,
points?
yes. Yeah, so interestingly, there's a whole, so these formulas for these volumes, one can get formulas. So the question here is, what I didn't mention was that these spin structures have boundary behavior, and at a boundary point, the spin structure gives a spin structure on the circle. There are exactly two types of spin structures on the circle. I think, Kento, this is your question, that I've been restricting to the case where the spin structures are always never Schwartz, which means that they extend to a disk. So in particular, I have a forgetful map in my world with the Riemann, where they don't extend, I don't. But nevertheless, one can define these bundles and one can get volumes. In fact, now you can get genus 0 volumes. These bundles have lower rank than the bundle I was dealing with has rank 2g minus 2 plus n, but the bundle in general has rank 2g minus 2 plus n minus half the number of Riemanns. So these are the number of boundary components with this different type of spin behavior. And so one can indeed write down a collection of volumes for that, which are polynomials. And then as for the, what I tried to see is that they satisfy the same recursion, but so far I didn't see that.
Okay, yeah, thank you.
Hey, can I ask a question? It's actually continuation about what Kento already asked. So what I'd like to know, for example, if for this these pans, if the boundaries they become like 0, like the genus become like very, very like going to the infinity. So in the super case, as you mentioned, this geodesic, they don't cross. But it's work when we have a boundary. But when it's going to the infinity, that they look like they go to the like form of the genus. So how would be the behavior of this geodesic that they have to really cross them in that point?
So one thing I didn't understand, are you suggesting the genus is getting big?
And like the boundary getting like
Probably the length of the
the length of the boundary is getting big. Yeah, look, I find that interesting. So it ends up that the what I haven't spoken about underlying Mesiconus theorem is what's known as the McShane identity. And when one looks at very long boundaries, the McShane identity simplifies. So actually, let me just speak, with this pair of pants. So this pair of pants here, how this geodesic behaves as you leave it orthogonally, if you have very long length geodesic, just because of the area is fixed on a hyperbolic surface and you have a long geodesic, this sucks all of the area out and forces it into like a fat graph, a very thin surface. And what it means is the behavior of these geodesics is very easy to understand because they're basically just heading close to their boundary. If you try this in the super case, well, I couldn't get, for example, I got the McShane identity. So again, I'm using something I haven't used here. So just the behavior here, it diverged. So I not only didn't get nice behavior, I also couldn't take the limit. So what I'm saying is I find it very interesting, but I didn't understand how a long length geodesic in this super case functioned because I got something that diverged.
And another question about the tau function. Maybe you mentioned and I missed. So I want to know, can you get the normal KdV tau function of the normal case from this one? If you have you put the constraint or any limit or something, can you mention how you can get the normal tau function?
I think the answer is one can't. So you're asking for so there's a family of tau functions. I think where, look, Sasha Alexandrov, I think I saw him here. He will know if there's a family that includes Bresengross-Witten, Kontsevich-Witten, but they are very different. So, so the answer is, given this super volume, and let's change the question. If you know something about the super volume, can you know something about the Kontsevich tau function, Kontsevich-Witten tau function? I'd say no.
Okay, so of course, I have many questions, but but probably one of is that I always had an impression that actually in Mizrahi and Mach-Schein identities and in this construction, there is something more than just Kontsevich-Witten KdV tau function. And the same as compared to your construction and Stanford-Witten and just BGW tau function. So it was, I had an impression that the tau function is in the sort of limit of this construction. But now you state that they are actually equivalent, these two states. This is very interesting. Does this mean that in some way, having this BGW tau function, we can reconstruct this supersymmetric with Stanford? What do you think?
Okay, so I'm not at all the right person to answer that. What I can say, I think, is that I never see in the super world people talking about hard edge behavior. They in the matrix model, they get this super construction. I would have expected, if what you're saying, that this Bresengross-Witten is somehow fundamental to the super world, I would see somebody using the word hard edge behavior in matrix models. So so I am, like I said, the wrong person to answer that, and I would have expected, if there was something there, I would have expected.
Oh, no. Just, you know, your gut feeling. What do you think?
Oh, I would have expected. You said reproduce super from Bresengross-Witten. I would have expected something about hard edge behavior and super to come up, and it didn't so far. So my gut seems to be wrong.
No. It's really intriguing. Yes, I agree. So maybe we more questions first.
I have. Can I ask a question, Paul?
Yep.
So for you were saying, so if you have Riemann mark points, then the theta class does not vanish. Is that correct? So it's not like the Witten, R-spin class or something.
Sorry,
if I have, yeah, sorry.
It's not this theta class. What you're saying, there is a bundle, and one's taking the Euler class of this bundle. Okay. And so then what I said was in genus 0, it's now not too big. And so, for example, there are genus 0 volumes. When you say not anyway, so maybe re-ask.
Yeah. So yeah, exactly. So that was kind of the question. So if I take the bundle with Riemann twists, so if I have twists at the mark point, and then I take the top class, the top Euler class, even in genus 0, this does not vanish. Right?
Correct. Yeah, sorry. So just because it's the right degree, the question, does it not vanish? I've calculated and got non-vanishing numbers. Yes.
Okay.
Okay.
Can I ask a question?
Sure, Ezra.
Yeah. So do Stanford and Witten have a Virasoro which characterizes their tau function the way it works for the bosonic theory?
when
Or
you
do
say
you?
their tau function, I mean, the only tau function that comes is the Bresengross-Witten. They don't
Right.
describe a tau function actually in their work.
Oh, okay. Because I'm just thinking of the way Mezicani approached it. She, of course, didn't establish the ADV hierarchy. She established the recursion that emanates from.
But in fact, exactly, that's what happens here. It goes via Virasoro.
Yeah. Is there any way you can quickly, I mean, this Virasoro, are there any salient points that we should know about it? Or is it just?
Well, I totally recommend reading Sasha Alexandrov's papers, but it looks very much like a shifted, the Virasoro for, it looks basically the same as the Virasoro for Kontsevich-Witten, and just with a shift and missing, say, L-1. So they hardly look different.
Well, we have a disagreement actually with Sasha about this, okay? Because in my impression, there are only two models, Kontsevich-Witten and BGW, and all others, actually all other occurrences, they can be reduced to one of them. Okay, okay, so probably we have to continue to move. And first let's thanks again, Paul, for this very interesting talk, really, from the bottom of my heart. And for joining us in this very late evening in Melbourne. And now we move to the afternoon in the UK.
Lena, if you allow me, I will stop recording and then resume it in order to have separated records for each talk.
Of course, of course.